Concentrating solar thermal power technology, known as CSP, generates electricity by using mirrors to reflect and concentrate sunlight onto a receiver, where a fluid is heated, stored, and then the thermal energy is dispatched to power a turbine. Traditional power cycles use steam as a working fluid, but advanced turbines that use supercritical carbon dioxide have the potential to be lower cost, higher efficiency, and utilize dry cooling, which helps to conserve water. But before these cycles can be incorporated into today's CSP plants, we need to understand the parameters and constraints in order to minimize costs and maximize power output. How can we use machine learning and optimization techniques to reduce the cost of incorporating dry cooling into a CSP plant?
Yeah, so hello everybody, and welcome to the CSP Cool Optimization team. I just want to congratulate all the teams before us and also after us to start off. It's been a wonderful showcase, and I just want to hope we can continue on with this. But to start off with, I'm going to introduce our team here. First, myself, Sean Hatcher, and then followed by Andrea, Bernd, and Will, and then along with our wonderful faculty along the bottom. And we're going to go ahead and start. And we're going to start off with the energy demand problem that we have. Currently, the main renewables we have, such as wind and solar panels, don't have the capacity to meet the demand that other dispatchable resources have. And so we use these fossil fuels and other energy sources to meet this demand at the same time. And so this is not a very sustainable way to go forth into the future. So what we're going to try to do is implement CSP. Now, what is CSP exactly? Well, first off, CSP uses in a whole field an array of mirrors to focus sunlight onto a receiver, which is going to heat a fluid, which is going to in these thermal storage tanks, which then goes to generators, turbines, and so on to the grid. Well, the main component that CSP is that we're trying to implement here is that it's a dispatchable energy source. It's able to have the storage tanks up to 10 hours of just for day and night and for peak demand. So we're hoping that we can implement this CSP into the non-dispatchable sources, like I said earlier, with the panels and the wind turbines, to meet this new demand that we have in the energy crisis. And so, first off, why do we not use CSP yet? Well, first off, it's very, very expensive. Here in the last decade, it has dropped drastically, however, and we're trying to reduce that cost continuously. But right now, steam turbines use a lot of water, which is quite expensive, and the turbines in these plants are massive. And so, where CSP is most readily available is going to be in the desert, very dry, arid regions. This place is going to be very costly for water and other implementations for steam. And so what we're going to try to do? Well, we're going to try to implement air cooling instead, along with a new technology such as supercritical CO2. We're withdrawing all the water out of the system and using the new air cooling and supercritical CO2 turbines to actually produce this new, more cost-efficient energy production. And so with that all being said, I'm going to pass it off to Andrea to discuss Team Solair's optimization results to reduce the cost in these dry cooler.
All right. Yeah. So thanks, Sean. So what does Solair do? So, well, the technology is so new that we really started building something from the ground up. And we gathered some data about weather in different cities in the US, physical correlation describing the heat exchange in the dry cooler, and cost data from Department of Energy and expert knowledge. And then these are the inputs to our simulator that we built that simulates the inner working of the heat exchanger, and then which is then used to optimize the design and ultimately come up with an optimal design. So how does the simulator actually works? Well, first we discretize the problem, both in the direction of air and in the direction of CO2, as you can see here on the left. And then depending on the design, so the diameter of the tube, the fins, and the fan power, we solve the thermodynamical equations iteratively. And this allows us to calculate with great accuracy the heat transfer coefficient throughout the heat exchanger and maintain the CO2 in supercritical state, which is very important for maintaining the plant working. And so with this, we can test any possible design, but of course, this is clearly not feasible because the parameter space is extremely vast. So what do? we need a clever way to iterate over these designs. And the way we do it is using a trust region Bayesian optimization technique, which is a very fancy way to call a method that cleverly selects where to explore the parameter space based on the level of trust that it has, that a minimum is in fact in that region. And this dramatically improves sample efficiency and with respect to other optimization techniques. And what this all machinery allows us to do is this. So the model starts with a random design that is far from optimal, and then it progressively improves the design, maintaining the CO2 supercritical and also satisfying the thermal constraint that are imposed by the power cycle, and eventually converts to an optimal solution in terms of cost. And now I'll pass it on to Will to tell you about how much better this solution is actually with respect to our baseline.
All right, let's take a quick look at our reference design, which is the current state of the art in terms of air cooling of supercritical CO2. And we estimate the price to be around $670,000 throughout the entire lifetime of the cooler. Now, using solar and our Bayesian optimization pipeline, we managed to bring down the cost all the way down to $197,000, which is about a 70% discount. Note here that the fans in these visualizations are the same size, so our cooler is actually much smaller than the reference. So not only is it cheaper, it's also much more efficient and compact. Right? So what's different between our optimal design and the reference design exactly? Everything is about 50% smaller, including the fin pitch, which deceptively enough means that there's a larger number of fins per unit length, and this is where we're getting most of our cooling efficiency from. Right? And here's a quick sensitivity analysis for how each parameter affects the cost. The way to think about this is that assuming all the other parameters are fixed, moving one parameter to its optimal value can give a reasonable discount. It's also possible it would actually increase the price. This highlights the fact that the cost landscape is highly nonlinear, and one really has to optimize over all these parameters jointly to get this combined 70% discount. And now I'll pass it over to Bernd to tell you about the future of solar.
Thank you, Will. So we've now seen that our solar air simulator gives us an optimized air cooler design for any location on Earth. To put this into perspective, I'd like to show you two global maps of the annual solar irradiance on the left and the availability of water on the right. You can clearly see that there's a lot of overlap between regions with large amounts of large amounts of solar energy and regions with small amounts of water. So what an optimization of an air cooler design allows us to do is it allows us to expand CSP to these arid regions where there's not enough water. We can also lower the cost of those plants, and it gives more people on the planet access to dispatchable renewable energy. So now I'd like to take a step back. As a species, we already have developed all of these beautiful renewable energy technology. We're now looking at a future where AI and ML methods will help us make use of these technologies in a better and more effective way. To make this happen, we are working closely with industry partners, shown on the top right, that are ready to take this to the field. Of course, there's still a lot of work left to do for us. We want to add more features to make our simulations more realistic, and we want to generalize our approach to include more possible designs. With that, I'd like to thank my teammates for their incredible work, our partners for their ongoing support, and all of you for your attention. Thank you very much.